Homegrown. Okay, thank you very much. So we have a problem with the microphone. Can everybody hear me? So if not, please complain if I should get less loud at the beginning. So the lecture, these 4 lectures, will be about multiple zeta values. And in the title I gave the elliptic already in parentheses. So there will be lectures on usual multiple zeta values and so-called elliptic multiple zeta values. So what is the reason we are actually thinking about those numbers? The reason is they are omnipresent in calculations of Feynman diagrams together with other numbers we believe are transcendental. But if it comes to naming a class of numbers which is most present, I think it would be the multiple zeta values which appear in different tastes here and there and in many different calculations of Feynman diagrams. So this is a lecture about numbers, but we'll see in the course of the lecture that these numbers will actually have representations as integrals, and many of the properties of those numbers can be derived from the representation of those integrals. They will have representations as infinite sums as well, and we'll encounter those and we'll explore those. So if you calculate a scattering amplitude, indeed you will get things like pi to the power 2k as a coefficient. So this is not about the dependence on kinematical parameters, but this is about the coefficients which show up in front of these parameters. So we can get something like pi 2 to the power 2k. We can get a logarithm of 2, for example. We could get something which is called Zeta 3,5 and will be one of the main players in exploring the multiple zeta values at the first 2 lectures. We could get something like 4/3 of logarithm of z, where z is a scale-free or unitless variable. But we could also get something like omega a, and I'll explain what that is. That's better, right? This chalk. Okay. Omega a of 3 to 1 of a parameter tau. Say again, please. Hab sie schon. Okay. So, yeah, I switched to the more soft chalk. I think that works better. Okay. So, in general, if we would start calculating interesting. If we would start calculating a Feynman diagram, we would decompose it into, or split it into loop orders. So we'll get a sum of L equals 0 to infinity of the amplitude at a certain loop orders labeled by some labels which I collectively simply call 1 to n. And then the whole process of sorting out diagrams sets in, and everybody knows the Feynman rules and the translation into the solution of a certain integral. And that is actually something you will hear from in Eric's lecture right afterwards. What happens after all is that you usually end up introducing Feynman parameters and write the individual objects A as a sum of certain integrals. And these integrals will have the following form. It will look like some prefactor of gamma functions which shows up after introducing the Feynman parameters usually, and you get some powers of or products of other gamma functions which contain powers of certain propagators. But the most important thing is that you can write these integrals usually in terms of Feynman parameters x. These Feynman parameters, they can be introduced even in a formalized way, and we'll have a delta function from j equal 1 to n. N is the number of the Feynman parameters xj. And then there is some product of differentials with respect to these Feynman parameters times xj to a certain power nu j minus 1. That's the same power which appears here. And then there is a ratio of two so-called Szymanczyk polynomials which are raised to some power. That is L d over 2, and here we have the same power, nu minus L d over 2. So in this formula, you will recognize a lot of the things you have for sure done yourself before. So the L is the number of loops of the diagram we want to calculate. D is the dimension, and we'll have to think, and that is also part of Erik's lecture, about whether this integral converges and whether we have to use dimensional regularization. All this will not be in this lecture, but the main point I want to make here is that these integrals can be parameterized in the way I wrote down. That is, we'll have to integrate over a simplex. That is, we'll have a set of parameters which usually are taken to vary between 0 and 1, and they are related by a delta function, and this delta function describes a certain simplex or polytope you want to integrate over. And now, practically, what you would do, you would start integrating these Feynman parameters, and you would select a certain succession of doing so and making sure that this delta function here is always satisfied, and that will lead to iterated integrals. That is, the parameter you will be integrating over will then be result in an integral which is then integrated over the next parameter. I will make more precise what I mean by iterated integrals, but the message to get across is the introduction of Feynman parameters naturally leads to the class of iterated integrals. And the iterated integrals will be the central object of those lectures here. They will be the starting point, and the classification of iterated integrals will actually lead to the classification of those numbers. So what is the logic here? We have a Feynman integral and then we take the Feynman parametrization and this will lead to a type of iterated integral. Now, I said at the very beginning, and I actually made a line underneath, we are talking about numbers. So in order to get from an iterated integral to a number, this iterated integral needs to be evaluated at a special point. And usually this special point will be just 1. And I'll simply write evaluation at z equals 1. That might not be entirely true, so I'll put it into quotation marks. There's other scenarios, but for now, this will lead to the numbers we actually want to have. And the logic I'm going to follow during these 4 lectures is I will first tell something about these iterated integrals. I will start with the so-called genus 0 integrals and then go to genus 1 and then derive properties and a couple of relations between these numbers. While doing so, my goal is that at the same time I want to provide the tools to play around with those numbers. So there will be, and in particular at the end of this lecture already, a part in these lectures where I introduce you to some concepts, how to deal with those numbers, first of all in Mathematica, second, get an idea how to get large expressions or many digits, very precise expression for the numbers to be evaluated, and Mathematica can do that, of course, and but there is better tools which can provide you with these numbers. And one goal of those lectures is to let you try these things and provide you with the necessary tools to actually get something running, to actually calculate 2 or 3 small experiments one can do with those numbers. That's actually one of the very nice things about those numbers. Many of the results can be, of course, proven. A lot more of the results cannot be proven. And many of them, in particular the conjectural ones, have been found out by experiment. So we are talking about people who played around with those numbers with the help of computers and found out beautiful relations and properties which are to a large extent not even proven nowadays. Now, what is the outline? I'll start with genus 0, and genus 0, of course you know what genus 0 is. Sounds like a very strange way of dividing the lecture in 2 parts, because the second part will be for genus 1. However, it is natural integrals on genus 0 and natural integrals on genus 1 we are going to consider. Roughly, it will be that the first 2 lectures are devoted to genus 0 and a collection of tools, and the second 2 lectures on Thursday and Friday will be about genus 1, because these are a little more complicated numbers. And we'll see that at genus 0, the class of iterated integrals I will consider will lead to multiple zeta values, and I will always write MZV for short for those. And once we are at genus 1, we are talking about EMZVs, elliptic multiple zeta values. Now, this thing here is a first indication that these numbers are not really numbers. So here's a tau in there, and this tau will be the modular parameter, or the parameter describing the geometry of the Riemann surface we will define the iterated integrals on. And that is actually the part where, when I thought about how this lecture could be constructed, thought that this is the part where the geometry actually kicks in. So these numbers somehow can be classified or categorized by thinking about the iterated integrals on a certain geometry, on the Riemann surface of a certain genus. Now, are there any questions up to now? That's the plan. No? Okay. Sure. I'm very sure, and I'm actually very curious. So let's discuss that at the end of the lecture. So what I would hope is that, of course, at genus 2, and it's actually pretty clear from the structure that at genus 2, you will again find a set of numbers. These numbers better should depend on in the same way as the genus 1 numbers depend on something describing the geometry at genus 1, that should better depend on some, let's call them moduli, on the genus 2 Riemann surface. That better be 3 numbers, because a genus 2 Riemann surface is described by 3 ratios of cycles. So that might happen, and I'm sure it's going to happen. But the number of results on those numbers is very rare. It's very small. Okay, so let's get started with genus 0. And I want to consider iterated integrals on CP1. So I'll consider integrals on the Riemann sphere. And what I want to do for getting started, I want to integrate polynomials or rational functions along some path on the Riemann sphere. And for simplicity, I would like to take a path along the real line for now. So let's say here's infinity, here's 0, then here's 1 on the complex plane, and somehow around this circle I want to integrate. The whole theory can be developed for any integration path on the Riemann sphere, but for now let's just confine ourselves to this simplified situation. And if you now take a rational function on this Riemann sphere, you might use all the tools you're very well aware of. You can take derivatives and consider partial fraction. You can integrate by parts. And what happens is that you are left with 2 things which are obstructions, or things which cannot be further simplified. That's the poles. That's the integral dx over x, or dz over z, depending on how you want to call it. And that will lead to the logarithm of x. And the second thing is you might have a shifted pole. So you consider the integral dx over x minus ai. And ai is the position of the pole, obviously. And this is nothing else as log of 1 minus x over ai. And there's nothing you can actually do about it. There's nothing you can get around, and it's also clear. And I hope Eric will comment on that, that in these iterated integrals, you will get something like a meromorphic function. A meromorphic function will have poles, and somehow one will encounter those poles. Now, what do people do if they encounter that kind of problem? They will just phrase them nicely and define iterated integrals. And these iterated integrals have been the main players in many fields of amplitude calculations during the last couple of years, maybe even decades. So they are defined in the following way. It's a capital G here, and these integrals, they are just the iterated integration over many of these poles here with the associated differential form. So that is an integral from 0 to z. Z is the argument here in the function dt over t minus a1g of a2 to ar. And together with the starting point for this calculation, where you would define that the empty integral is just 1, we have defined a class of functions. And it turns out, and one can think about it, that this is the really canonical and also sensible class of functions on genus 0 on the Riemann sphere. Now, let's assume that we have a Feynman integral whose calculation we can bring into this particular form and assume something more. We somehow find a collection of these iterated integrals. Then the immediate question is the question of whether one can find a canonical representation. And during the first SAGEX school in the lecture of Claude Dour, you have been already encountering this type of polylogarithms. So that's one logarithm, and if you integrate several times, then you get a polylogarithm. And then you, the question to be asked is, what is the functional relations between these integrals? Yes? Thanks. Yes. Indeed, the t needs to be here in the argument. Thank you. Okay, so there's numerous techniques available, and I'm sure Eric will talk about some of them for certain classes of iterated integrals. Let me be very careful here. Nevertheless, there's a lot one does know actually about these integrals. One also does know a lot about these integrals if these a's here might be not numbers, but rational functions, for example. And that is the realm of the symbol and the letters. That is something I'm sure you have heard of already. Now, numbers are easier than functions. And so I don't want to talk about the functional relations between those integrals, but I'd like to restrict my attention to a particular type of these iterated integrals. And the type I want to restrict my attention to is that I choose the elements ai from the set 0 and 1. These are not the harmonic polylogs. If I would consider harmonic polylogs, I would also allow a -1 here. But for getting straight away to the multiple zeta values, let's confine ourselves to indices 0 and 1. And that leads to identities like G of 0, 1, 0, 0, 1, 0, and 1, evaluated at 1. And this is just minus zeta of 2, 3, and 2. I'll define that properly. But this is to give you a first impression of what the objects are we are actually dealing with. The multiple zeta aficionados might recognize that I chose a symmetric labeling here. I will talk about how to properly do that. There's also a minus sign here. But what you can recognize already here, in the label of these iterated integral, you have blocks with zeros and ones, and the block starting with the 0 and then 1 is of length 2, the next block is of length 3, and the next third block is of length 2. And that might have to do something with the numbers I wrote here. Now, that is, there seems to be an integral representation for these multiple zeta values. However, multiple zeta values are already around for a couple of decades, but what people recognized before, and that is the point where I want to switch back a little in history, was single zeta values. And these single zeta values, they are actually very simple objects. So how are they defined? They are defined as zeta of k is just the sum of n equal 1 to infinity 1 over n to the power of k. And you better set k larger and equal to 2, otherwise your sum terribly diverges. And indeed, this is the numbers I'm sure you have seen numerous times. One can find nice identities. For example, zeta of 2 is pi squared over 6. And just to give you an idea, this is 1.645 approximately, of course. And then you get zeta of 3, which you can calculate and will talk about how to calculate that. 1.202 as zeta of 4 is just pi to the 4 over 90, and it goes on. And for the idea of it, zeta of 20 is proportional. I don't know the precise number. I should have written down it. It's pi to the 20, but the thing I want to get across, it's basically 1. So we get 1 plus, or
You don't want to write it down.
say again?
You don't want to write it down.
You are live calculating. No, I think I found a good way. It's 1 plus 1 to the 10 to the minus 7. So it gets very close to 1 very, very fast. Now, this is a little funny structure. All these even zeta values seem to be related to powers of pi, and the odds aren't. And of course, people have come across that pattern, and it was actually Euler, Leonhard Euler, in 1743, who proved that zeta of 2k is nothing else as minus the 2kth Bernoulli number times 2 pi I to the k over twice the factorial of 2k. Now, yeah, one can calculate these numbers, and also Euler knew what the Bernoulli numbers were, of course, and the Bernoulli numbers is something you get from a generating series, and you can take a series expansion of t over e to the t minus 1. It's not correct?
No, the upper one is the 2 pi I to the 2k.
Yes, it is. Thanks. Yeah, it better be. Yeah, so the Bernoulli numbers you get with t over e to the t minus 1, and if you expand that, one can show that, or that is actually the definition, that that's the sum over 0 to infinity bn t to the n over n factorial. And now these numbers, let me write down the Bernoulli numbers. And then there is Bernoulli number 0, 1, and 2. And this is 1, this is minus 1/2. And B2 is 1 over 6. And it goes on for a little. The only Bernoulli number you actually need to know is 691, because if you recognize that in your calculation, and we'll do, I shouldn't promise that, but I'll try to come up with a neat example where the 691 guides you the way that something has to do something with the relation of zeta values and powers of pi. So it's a prime number, 691, and it appears, I think, as the 12th Bernoulli number. Okay, so how would one actually prove that? It's an actually very old and very nice and elementary proof, which I will just sketch in order to make sure that I mention that all these relations here are very beautiful and deep relations. So one can prove that the zeta 2k is an element of q, or is q times pi to the 2k. That's basically what you can already see with the numbers, and that is valid for all k larger and equal to 1. And how does one prove the validity of that formula? One takes, and I shouldn't write proof, so I rather write sketch here. one can take the pi times cotangent of pi times alpha and expand that or write it as 1 over alpha times an infinite sum n larger than 0, 1 over alpha plus n minus plus 1 over alpha minus n. And now you can consider the right-hand side and the left-hand side of that equation. And indeed, it turns out that the right-hand side can be written as a different series. So you basically convert these two terms, the 1 over alpha plus n and the 1 over alpha minus n, into a geometric series. You properly collect terms, so to geometric series, properly collect terms. And once you've done that, you'll get something like 1 over alpha minus sum over k equal 1 to infinity of 2 zeta of 2k to the alpha, or alpha to the 2k minus 1. That's already what you want. And the left-hand side, at the left-hand side, you write down the exponential representation for the cotangent. So this is e to the pi I alpha plus e to the minus pi I alpha over e to the pi I alpha minus e to the minus pi I alpha. And this can be, by just taking an exponential out, rewritten as pi times I times 1 plus 2 over e to the 2 pi I alpha minus 1. And if you now take a series expansion of that expression, you will exactly end up with the right-hand side using the definition of the pair of Bernoulli numbers. So that's a very elementary thing, and I think that is the only proof I will actually write down in full detail here. I shouldn't say that, but it is one of the very few proofs I will write down in full detail.
Sorry, is that formula there also proof one Euler's formula?
Say again, please. Which formula?
Euler's formula there, that also kind of proves it.
That is the proof of the Euler formula. So if you take two different expansions of the, or two different representations of the cotangent and expand them properly, then your result, if you compare, so let me write it down, the last step. So that is 1 over alpha plus sum over k equal 1 to infinity b 2k 2 pi I to the 2k over 2k factorial, and then there's alpha to the 2k minus 1. And then you compare the coefficients, and by comparing the coefficients, you can show that for each power, you need to have the equality between the two sides of the equation. Okay, let me wipe the blackboard. Say again, please.
There should be an extra alpha in the equation.
There should be. Why should there be? Really? So we have 1 over alpha, and then we have alpha to the 2k minus 1. So with k equals 1, we get. I'm sorry. Maybe it's a little too small. I'll try to write a little larger. This one, this is, yeah, thanks again. Okay, I was a little too fast here. Now, so that is single zeta values, and these zeta, they are also can be shown to be of course related to the Riemann zeta function, but if it comes to more precise statements about these single zeta values, then very little is known. For example, one would like to know whether they are algebraic numbers or possibly transcendental numbers. And there have been a couple of proofs, some of them rather recent, and they are actually, given that one would like to have statements like all these numbers are transcendental or they are transcendental of some weight, they are very small results, despite the fact that they have been very difficult to obtain, so they are actually large results. So one does know, or one would like to know, that pi and zeta 3 and zeta 5 are algebraically independent, but the only thing one can really prove is that zeta 3 is irrational. That's a proof from Apparit from 1977. And then there are such nice statements that, for example, that there's an infinite number of odd irrational zeta values. Yeah, I can believe that. And also one can show, and that was a proof from 2004, that one among zeta 5, zeta 7, zeta 9, and zeta 11 needs to be irrational. Proof of transcendence doesn't really exist. Now, would be done with the lecture if it was only about these single zeta values, but of course there need to be multiple zeta values, and the definition is an obvious extension of the sum definition of the single zeta value up there. So I'd like to define zeta of n1 to nr as a nested sum where 0 is smaller than k1, smaller than kr. So I'm summing over a set of ordered integers, 1 over k1 to the n1, kr to the nr. That is, the arguments of this function appear in the exponent for these integers, and you sum over all of them up to infinity. I should, first of all, write down what are the realms of validity. The last r, or the last nr, better be larger or equal to 2, otherwise you don't get a convergent expression. For completeness, n1 to nr should be element of the natural numbers, and I will call the expression n1, or the sum of all the arguments, the weight of the zeta function, the multiple zeta value, and r the depth. A word of caution is necessary here, because there is many places during this lecture where you can have different definitions in different papers. So this definition is the one used by Francis Brown, for example. If you look at a very classical paper of Kaneko, for example, then you will find the ordering of the integers the other way around. So whenever you are not able to prove something, the first thing to check is whether maybe the ordering of the integers is defined in the different way. If you want to match some numbers and you don't find the expected value of zeta 3,5, there's a good chance you better look at zeta 5,3 in the other convention, and then you got it. Okay, one can actually rather easily prove that this sum converges for all the situations I've been writing down here, but I don't want to do that. At the beginning, when I introduced these iterated integrals on genus 0, I mentioned that everybody would basically start looking at relations and functional relations between these iterated integrals, between these polylogarithms. And while I was not answering any of those questions up there, I would like to ask, are these numbers really independent? So can we actually perform some manipulations to the sum in order to derive relations between zeta values of these different indices? And of course, I wouldn't ask that question if the answer wasn't true, wasn't yes. And so I want to start with an easy example, and this example will lead to something called the Staffel relations. So let us consider two zeta values which are single zeta values. So we take zeta of n1 times zeta of n2. Writing this as a sum, we can write it as the sum over k1 and let me call it k and l. K and l equals 0 to infinity. So of course no ordering is implied here because I'm just multiplying the two expressions for the sum. So this will be 1 over k to the n1 times l to the power n2. The idea between these Staffel relations is very easily explained once one considers simply lattice. So when you perform that sum, you start from k and l. Let me call that k, and that l equal to 0, and then you start to work your way up. Either you first iterate in k, then you iterate in l, and you get a lot more evaluation points here and there, and so on. And clever people have split the sum into intelligent pieces, or the pieces itself are not intelligent, the people are intelligent, but it's intelligent to split it in the pieces. So you want to have a diagonal piece which is the sum over 0 less and equal one should better actually start with larger than 0. So one starts with 0 less or equal 0 less than k equal l to infinity. That's the diagonal piece. And then one will take the upper triangle and the lower triangle, and of course we'll also get some pieces here and there. So now we have 0 less than L less than K plus the sum 0 less than K less than L. And this is to be multiplied with 1 over K to the N1 L to the N2. But this already looks very much like the definition of multiple zeta value, and indeed we can write down what that actually is. So here we'll have a zeta. If k equals L, we can combine these two terms. We'll have a zeta of n1 plus n2 from the first sum. And then there is a zeta n1 comma n2. And did I have it the right way? L smaller. No, it's an n2, n1. And then there's a zeta n1, n2. And that's the first example of a relation between those zeta values, which very easily follows from the sum representation of the zeta values. In fact, these Staffel relations are most naturally considered in the sum representation, while the other relations, the shuffle relations we'll look at in a minute, are most naturally considered in the integral representation I'm going to introduce soon. Now, let's have an example. And I write down this example because that could be one of the first things you might want to check using Paris or Mathematica later. So easily you can write down zeta of 2 times zeta of 3. And this is zeta of 2, 3 plus zeta of 3, 2 plus zeta of 5. And the numbers, that's 1,977, we'll get a 0.228, and we get a 0.711 here, and a 1.036 here. So one can check that this is actually correct. Nevertheless, of course, if the calculation is correct, then it better be. Now, you can now think about something which is not with two indices only, but you can consider sums over simplices or of different ways of dividing your unit cube in different polyhedra. And the statement is this type of sum manipulations extend to all numbers of zeta values. Usually that is one can formalize that, but I would like to stick with an example here because one can always do it piece by piece. So one can start with factors of 2 zeta values and then add another one. So this is one type of relations. That's the Staffel relations. Now, for the shuffle product and the shuffle relations, I need to introduce some notation which secretly was already around. So the most important identity, which was also the starting point of what I told, is that the zeta values, the multiple zeta values, are related to these iterated integrals G. So the basic relation is that zeta of n1 to nr is -1 to the power r. R was the depth of the multiple zeta values. That is the number of arguments in here, times G of 0, 0, 1, 0, 0, 1, evaluated at 1. So I'm putting a semicolon here in order to divide the argument from the other long row of labels. And the number here, that is the collective number of zeros and ones. So it will be a lot of zeros and exactly, precisely one entry 1 is nr, and this one is n1. So we can look up here. Here we have 2, here we have a 3, and here we have a 2 again. And I made a comment about the fact that I used a symmetric zeta here. So in that case, it is important to note that the last index of the zeta value is on the first position of these g's. Now, I can write this g as an iterated integral. So I can take some variables, 0 less or equal to ti less or equal to ti plus 1 less or equal to 1. So that is the way I want ordered differentiation variables in the interval 0 to 1 to appear on the blackboard. And then I can write dt1 over t1 minus 1 dt2 over t2, and then end with dt n1 over t n1. And that is the integral representation of the n1 block. And then I continue until I reach dt of the sum over of all n's. Let me just write w here over tw. But that's not the end. You might see, and I'm introducing that because I will recommend at the end that you take the effort and actually look at one of the zeta value lectures which are available. I will introduce another notion of integrals. One can write this same thing as the integral from 0 to 1 over omega 1, omega 0 to the n1 minus 1 to omega 1, omega 0, nr minus 1. I want to remind you that nr was larger and equal to 2. We want, for now, the integral to converge. And here I've defined two differential forms. Omega 0 is just dt over t, and omega 1 is dt over t minus 1. Again, here, a word of caution is necessary. Many people define omega 1 as 1 minus t. Others keep it t minus 1. And that is the source of many of these terms minus 1 to the r. So when you're missing minus 1 to the r, check the definition of your omegas. But in this omega language, and that's the last integral notion I will introduce, lots of mathematicians actually use an object called capital I, and this has 3 slots for arguments. That's the lower value of the integration region. Then comes all the 1 zeros to the n1 minus 1 up to 1 and a lot of zeros again, nr minus 1 and a 1. Say again? So there's another representation of these. There's a 0, a semicolon, then there's 1, 0 to the power n1 minus 1. That means that one has several zeros in a row. Then comes a lot of these blocks again, which are of length n1 or n2, n3, and so on. And the last block is of length nr, and you have 1 and nr minus 1 zeros then.
So that 0 is to say the start of the integral that like normally was given for granted that we were putting just one thing, just a 1, and now we're putting also...
Exactly. And unfortunately in this lecture we will not encounter why this is a very useful concept to have an index which is an index with the number 0. But if you think about polylogarithm identities or proving some symbol identities, that's a very good thing to have. Okay, so now I introduced this integral representation, and I want to write just another line for this system or these number of equations, because if you think about the fact that you have an iterated integral there, then you can think about what happens if you want to change the succession of your integration variables, for example. And an immediate result you can derive, and that is something one might actually, if one is happy to do that, simply do. It's a 2-line or 3-line calculation. You can derive that this integrals with the 0 and the 1 limits can also be written as 1 to the power nr minus 1, 0, then a couple of these blocks, 1 to the power n1 minus 1, and 0 and 1. That is, you can swap 0 to 1 minus 0 or x to 1 minus x. That's easily to prove in the representation you mentioned, where the omega 1 is just dt over 1 minus t. Otherwise, you will have to keep track of the minus signs. So that's already one important identity. Okay. Now, let us consider two zeta values, both with a set of indices, which I will denote with an underscore. So let's consider zeta of A and zeta of B. And these sets of indices is again such that AI is an element of 0 and 1, and BI is also an element of 0 and 1. So shuffle relations works with the index set 0 and 1 most easily, while the Staffel relation works with natural numbers and no zeros. So let's consider zeta of the set A times zeta of the set B, and this is and can be shown to be zeta of shuffle of these two sets. Who is not aware of what shuffle means? Everybody knows what shuffle is. I should better say it again. So shuffling is indeed exactly what you would expect from the name if you shuffle a deck of cards. So this denotes the set of all permutations of A and B, where you keep the individual ordering of the elements A and the elements of B intact. So you are allowed to mix A and B up, but you're not allowed to change the succession of each of the elements in A and each of the elements in B. I think that's most easily demonstrated by an example. So let us consider zeta of 2 times zeta of 3. That is, I wrote it in the natural numbers basis. That is converted to the 1 and 0 basis, zeta of 1, 0 times zeta of 1, 0, 0. And this will now be the sum of all ways of shuffling these numbers without interchanging the individual ordering. So the result will be 6 times zeta of 1, 1, 0, 0, 0, plus 3 times zeta of 0, 1, 0, 0, 1, 0, 1, 0, 0, plus 1 zeta of 1, 0, 0, 1, 0. And converting back to the original way of writing, this is 3, we get 3 zeta 2, 3 plus zeta of 3 and 2. That's again a relation. And one thing you might recognize is that the number of the or the weight of the zetas is additive and is actually conserved. So whenever you multiply two zeta values, then the total weight, which is 5 here, will be 5 for each of the multiple zeta values on the right-hand side.
So that's different from what you had before, so I guess that's a new relation.
That is a new relation. That is a different relation from what I had before. Yeah. So here we had a zeta 2 times zeta 3, and on the right-hand side we had a zeta 5 there. And here we have a 1,4 zeta. Neatly enough, of course, you can obviously relate zeta 1,4 to zeta 5 then. And that is the next statement I would like to do. One conjectures that all relations between multiple zeta values can be derived from combinations of these shuffle relations and the Stuffle relations. There is something with so-called cusp forms, which I don't want to comment on, but one believes that all these relations can be traced back to shuffle and Stuffle relations. And that goes usually by the name of the double shuffle relations. So when you do precisely what Luke suggested right now, if you write down suitable Stuffle and suitable shuffle relations and then compare them, you get the double shuffle relations. So you would actually consider the two ways of multiplying zeta values independently and then compare the results and get linear relations. So I already mentioned that somehow the weight is conserved within those identities, and that can be made more precise in the following statements. The first thing I want to suggest, and that's not my suggestion, but the suggestion of many mathematicians, I want to consider the number 1, which is, of course, a rational number, as a zeta value of depth and weight 0. That will make a couple of things easier when we are proceeding. And then I would like to define a space Z, curly Z, which is the Q-span of all zeta values and that is to be considered as a subset, actually a subalgebra, as one can show, of R. And then define furthermore Zk as the set of zeta values to Kd such that the K1, I should write n's here, such that n1 plus nr equals n. So I want a space where all zeta values are of the same, I'm sorry, I should write k here and k here, where all zeta values are of the same weight k. And the conjecture is that one can describe the space of all multiple zeta values as Z equals the sum over k Zk, but this wouldn't be too surprising. But what I want to show that, or what, no, I can't show that, but I want to dwell on is that this is actually a direct sum over all the spaces Zk. What does that mean? Well, that means that one believes and conjectures that there are no non-trivial co-linear relations between multiple zeta values of different weight. So we'll never get a relation which relates zeta 5 to zeta 2. So they are independent over Q. And many of the calculational statements we are going to explore in the following will rely on this particular fact. And the last theoretical thing I want to write down is that one actually also has a conjecture on the dimensions of those spaces. So a further conjecture, let b d0 equal 1, let d1 equal 0, and let d2 equal 1, and let dk equal dk minus 2 plus dk minus 3, then the dimension, of course, again, the Q dimension of Zk equals dk. That is a conjecture by Donzagier. And if you look at this, this is something which looks very much like a Fibonacci series. It's just that you don't use the predecessor and the predecessor of the predecessor, but you shift one more. And the first numbers, yeah, it's just dimension, the k and the dimension. So if you 1, 2, 3, 4, 5, 6, 7, 8, 9, then it's 0, 1, 1, 1, 2, 2, 3, 4, 5, and 7. You can also write that as the coefficients of a generating series. The generating series you want to consider is 1 over t cubed minus t squared minus 1. And if you consider the coefficients, you will get exactly the numbers in the lower line. Okay. From when? When did Zagier come up with that? In the 90s, I believe. So Broadhurst-Kreimer, I think Broadhurst-Kreimer, the refinement was in 97, is that correct? So Zagier was a little before that. So not before 70, somewhere late 80s, early 90s. I can look it up for you. Yeah. Now, there is 20 minutes left, and these 20 minutes I would like to use for making a couple of comments on numerical implementations of these zeta values. So now you got the basic tools, you got a couple of examples for two types of relations, and I already mentioned that many of these relations were known before they could be proven. Many relations are still known and cannot yet be proven, but numerics is a very valuable tool here. So the first thing I want to mention is, of course, I'm not sure of whether this is of course, but it's Mathematica. And Mathematica, as it has a solution for many things, will also have a solution for zeta values. So zeta, and that's supposed to be a computer font, zeta is the Riemann zeta function, and right away if you type in zeta of 2 into Mathematica, it will deliver pi squared over 6, so it knows all the things, it knows about Euler's, which is not there anymore, relation, and describes everything in terms of powers of pi. If you type zeta of 3, then Mathematica will not attempt to evaluate, but simply leave it as a number, and that continues like that. The downside is Mathematica doesn't have an implementation for multiple zeta values. Too bad. Yeah? So you might actually think about or try to let Mathematica calculate your zeta values. So what would you do in that case? Yeah, you would use something like take a sum, sure, then take a running variable I and take it to the power of -2. Let's calculate zeta of 2. And then do the following. Let I run from 1 to some number, which I will specify, and then write down n. So is somebody not familiar with the basic syntax of Mathematica? Then I'm happy to explain what I'm doing right now. Yeah? Okay. So let's look at this one. This is an implementation of a sum sign. Here is the I was tempted to say the integrand. That's what you sum. So I sum terms of the form 1 over I squared. And this parenthesis here tells you where I runs from. I runs from 1 to a number which I want to specify later on. So this is this hash is a placeholder. And the /n tells I want a number out. So Mathematica will try to calculate analytically or keep the expressions as long as it can. And here I advise, once you have the sum written down as a sum of a lot of ratios, then evaluate it numerically. And this whole thing I might actually map to some range of numbers. And I'm aware of the fact that this might be a little difficult to decipher, but that's something to probably try out. So this thing here gives me a list of powers. So if I take range from 0 to 6 and map 10 to the number of 0 to 6, this will produce a list which is just 10 to the 0, 10 to the 1, 10 to the 2, up to 10 to the 6. And this list of numbers will be plugged in here, and I will calculate 7 sums. And why do I do that? I want to show that convergence of that formula is very bad. So if I do that, and I'll get a list of numbers, and this list of numbers will be something like, so what is the first one? If we just take one element, then we get 1. The next one is 1 point, I can't remember what it's something like 1.5 and a little, and then we get 1.6 and something, and so on. And the statement is that you need to consider 10 to the 4 terms at least in order to get the 4th digit of the actual value, which is 1.644 something, 645, correct. So this is very bad convergence. And secondly, this is ridiculously slow. If you want to try it, you can actually put the n right here. Then you get a speed up of a factor of 100, because Mathematica internally tries to simplify all these fractions and tries to find a common denominator and write it in a nice form. You don't want that. You basically put it into numbers right away. So we are actually talking about a factor of 100 here. Now, this is how you would do it in Mathematica, and that is not a very nice way. In particular, yeah?
Euler calculated it numerically by hand.
Yes, he did. Yes, he did it more efficiently and he did more cleverly than just adding the sums. He took the two-tail solution, which is actually something which is implemented in either Paris or SAGE right now. So, of course, one can do better than that naive thing. I just wanted to point out that this is not the way to go. And this is, one last comment for Mathematica. You can tell Mathematica to be more precise if you take the working precision parameter up. So usually the working precision in Mathematica is machine precision. That is, the numbers usually have 15 more or less reliable digits. You can put up the working precision up to 100 or 160 with very little noticeable slowdown, as long as you don't diagonalize matrices. But for this type of thing, you can set up the working precision to your needs. Having said this, 100 or 160 digits is for experiments with zeta values a rather low number. So if people are considering multiple zeta values of high weight, say 20, 25, whatever, we are rather talking about something like 8,000, 10,000 digits, which you will need for numerical experiments. So if you ever have a nifty, beautiful question on how to deal with these things, then definitely David Broadhurst, British mathematician and physicist, or he's a physicist by education, will be very happy to talk with you about what the number of reliable digits depending on your algorithm is. For now, the statement is it needs to be rather high, but not scarily high. So people wanted to actually do better than what I just wrote down with Mathematica. And particularly if you try to do the same thing with a multisum, you will die already with elements of depth 2. That is an absolute nightmare. And many of the more powerful tools for calculating the numerical values of multiple zeta values, you can find them in a software called Paris. And the inventor of Paris, we had a discussion, is actually Henri Cohen. And he has taken care for this software, which is basically a C library or C++ library by now, for I think 30 years, more or less. Now it is Karim Belabas who is taking care for it, and the software is hosted at the University of Lyon. And the web page, which is a large web page including installation instructions, is paris.math.u-bordeaux.france. And for those who are able and willing to use it, there is also a Git archive where you can download the software. Having said this, there's far easier ways. For example, Ubuntu comes with a package of Paris. It's called GP, so it's called GNU Paris. It's an open source software, and it comes with a couple of additional packages. Just install them all. It's tiny compared to any other, or almost all other packages. And what you will get if you start or launch the Paris, you type in GP into your console, and you will be presented some prompt, nicely enough. And the first thing you want to do is you want to tell Paris that your precision needs to be higher. And you do that by typing in /p, which is the command for precision, followed by a space, and then let's put it to roughly 200. And then there are two functions in Paris, and it is again Don Zagier who actually implemented the one nicely converging multi-zeta function. He told me at some point that he was actually with Henri Cohen doing that. So there's one function called zeta, which now with usual parentheses takes just one argument. Say you want to calculate zeta of 2, and that will give you the 1.645, I don't know what. Then there's a command called zeta mult, and this will take usual parentheses, then a square bracket, and then it will take nr down to n1. And here we have the first encounter of convention clash. So the n's are as I defined, and for Paris you want to type them in the other direction. One nice test is, in my notation, zeta 3 is equal to zeta 1, 2, and that's for each program a good way to test which convention it's using, because if you turn it around, then you get zeta of 2, 1, which is a divergent zeta, and numerics will not work. We'll talk about divergent objects next. Now, this is how you can create values for zeta values ridiculously fast. So I just made a test during lunch break on my computer and calculated zeta at weight 11 as zeta 3, 3, 5. Up to 10,000 digits, and it took this usual rather old laptop something like half a minute to do that. And that's actually an amazing thing to get 10,000 digits with that. So these are mathematically amazingly well-educated routines which work in Paris. It's, of course, not the only thing. Paris can do a lot more. It can work, for example, with modular forms to an extent which I never believed it would actually do. It's an amazing program. Now, with the combination of those two, you should be able, and I really want to encourage you to do that, to just go over the threshold of installing Paris and then doing a couple of small experiments. You should be able to verify all of the relations I wrote down and many other different relations. I will write down one last for you, and I will ask Jenny, the secretary, to send you a number. And this number is a rational combination of these zeta values. And while I'm going to introduce the concept of how to deal with those numbers and how to actually find out what linear combination of multiple zeta values it is, I will do that on Wednesday. You might already look up the so-called Psaq algorithm. I'll put it to the Mathematica section because it does have an implementation. So the buzzword is PSLQ. I will comment on this algorithm briefly. It is an algorithm which allows, given a certain set of numbers, which are given in a numerical form, it tells you the smallest integer relation between those numbers. So it is basically a linear tester over Q, if you want. And in Mathematica, it's called find integer null vector. Is that correct? Is it correct? I always use my, huh? I always use my own implementation. I've written it down somewhere. I'm sorry. Find integer null vector is the right thing. So, and here, as for the end of the lecture, is one relation which is a little more involved, and if you can test that one, then you are very sure that your small entry-level multiple zeta variant testing setup works properly. So there's a nice relation which is 28 times zeta of 3,9 plus 150 zeta of 5,7 plus 168 zeta of 7,5 minus 5,197 over 691. And here we have it, 691. Welcome to the world. Zeta of 12, and that better be 0. Okay, so what I tried to do today was I introduced you to iterated integrals and particular numbers, which are these iterated integrals, which are somehow related to genus 0 at z equals 1. And we explored for a little how relations between these numbers can be derived. We wrote down together or explored a couple of these relations. There were two types of relations, Staffel and Shuffle relations, and the conjecture tells that all the combination of those is able to provide all the relations between multiple zeta values of a certain weight. And of a certain weight comes with the statement here that we are actually looking at a graded Q vector space for the multiple zeta values, which is graded by the weight of the zeta values. And then there was the only addition, some dimension formula, which tells how large a basis of numbers for that space actually is. And at the end, I tried to help you to do a couple of first experiments with Mathematica and Paris. And I'm very happy to also help if something shouldn't work with installing this, or yeah, I hope I didn't have any typos. Okay, for the first lecture.
Is it clear or proven that multiple zeta values cannot be written as linear combination with rational coefficients of single zeta values?
That multiple zeta values cannot be written as, no, there's no proof, as far as I know. No, could be the case. So one should be maybe asking the question a little more precise. One could ask, is there a multiple zeta value which can be written as a linear combination of a single zeta value? The answer to that is yes. We have, for example, the zeta 3 equals zeta 1, 2 example I wrote down. But if one would ask, can any multiple zeta value be written as a combination of single zeta values, the answer so far is no, and I think it's pretty safe to assume it's no.
So this zeta 3 equals to zeta 1 over 2, you said all the relations come from Staffel or Shuffle.
Mm-hmm.
I mean, zeta 1 is infinity, right? So
Yes.
how would you get this relation?
Yeah, I'm happy actually you asked that question. So zeta of 3, we have no problem with that. And yes, zeta of 1 is infinity. So one has to think about a little larger space and extend the space of allowed zetas by doing something with the zeta of 1. And that is actually how the next lecture is going to start. So everything was with the zeta values which have n r larger and equal than 2. So the last index. And one can treat in the same way actually as one treats Feynman integrals which are divergent, treat zeta values with divergences and make sure that whatever in physics needs to be calculated will have canceling divergences. I'll talk about it exactly at the beginning of the next lecture.
Can you maybe motivate me to how you get to assume that these alphas in the zeta values, I mean, if you compute contour of polylogarithms, you usually have like symbols, alphabet, rational functions of kilometric variance. How do you get from there to natural numbers?
To the numbers 0 and 1. Yeah, okay. So why did I confine myself to looking at these zeros and ones? Yeah, so let me tell first that if you have Goncharov polylogs and symbols, of course, this is a larger space than the space of the numbers I'm considering. But it turns out that once you calculate a physics result, of course, you will end up with a number. And it is functional relations between these Goncharov polylogarithms which allows you, in many cases, to find an integral representation of the object you want to consider in terms of, which is similar or which is just a zeta value. So the upper integration limit was a 1 for the zeta values. And for example, you could do a transformation in your integral which actually makes the upper integration limit being 1 by introducing a certain scale, and suddenly you can factor the information of your external parameter out and get a number which multiplies some function of the external parameter. So the statement is fishy and unclear, but in very many cases you can manipulate your Goncharov polylogs in a way that you can somehow filter out or get some multiple zeta values. In other cases, you might get logs of 2 and other numbers, but in even more cases, you can get numbers. Let me put it like that. More? Okay.
Yeah, we're going to talk about log 2 and how it fits into this generalization theorem.
I might actually talk about log 2 at the very end if I have some time. So for now, I really want to stick with the multiple zeta values because they provide the techniques for elliptic multiple zeta values then, but yes, log 2 is the entrance in a very new and very large, interesting new world again, of course, for Euler sums and alternating, yeah.
The coefficient only out of the shuffling as a
Yes,
name, like
yes.
a function that you can use in Mathematica to...
Exactly. So it's not at the blackboard anymore, but for the Staffel relations, we had unit coefficients. So if you consider zeta 2 times zeta 3 and then do the manipulation with the sum in there, you get unit coefficient for zeta 2,3, zeta 3,2, and zeta 5. Now, here you can see that if you would give the zeros some marking, then there is a couple of different ways. Look, for example, at this first here, 6 zeta 1, 1, 0, 0, 0. If you take 2 zeros and 1 0, you have 6 different ways. You have 3 different ways of ordering the zeros, and you have 2 different ways of ordering the ones. So that makes exactly the 6 there. So you can actually express that explicitly in terms of binomial coefficients. A couple of proofs for these iterated integrals are taken that way. And the complicated coefficients here, they come from 2 sources. They come from exactly what you just said. And here the 691 is, of course, because I should better write something which is zeta 2 to the 6 that would make the 691 disappear. Because then I would have a clearer or a better number for pi squared.
So again, sorry, the homework is to use the software to verify
The
When you ask questions, also try to ask them loud.
What was the homework related to?
The homework is to get your hands dirty with installing Paris, getting some many digits numbers, and check that you can actually verify this type of relations. And then there will be a secret number. I think I'll send you a 1,000-digit number. And then you could use find integer null vector with a couple of candidates to find out what rational combinations of zeta values it is. So I think it's going to be sent tomorrow morning. I talked to Jenny already. Say again? Is there a prize? Let me think about that. If there is a prize, then I will make it a little more difficult. The one I have is rather accessible. So, say again? No, that would be mean. Calories. Yeah. Also, the energy consumption of the computer should be taken into account, right? So if you can do it on the first attempt, then you will be ecologically perfect. Otherwise, further questions?
Did you know you can get multiple zeta values from the cloud too?
Yes, you mentioned that. I actually didn't look it up. Can you say the address? Where it hit?
Well, it's a little complicated, but if you Google EasyFace, E-C-F-A-C-E.
This one?
You probably should put multiple zeta values too, otherwise you'll go to the wrong EasyFace.
So Lance is saying that there is an online source which probably uses some Paris or SAGE or whatever algorithm or...
Except it doesn't like to waste too much time, so if you put more than 100 digits, it just rounds it up to 100.
Too bad. No, I'm actually happy about that comment because that one will do forever. Yeah, okay, so you can get online numerical values, but be very careful what succession of labels they actually use.
Okay, so Johannes is also here for 3 more lectures to go, and we see all week. So
Yeah.
why don't we take a break now until 1:15, and let's thank Johannes for this great lecture.